Hello and welcome back to our last topic for CSCE 155H, that's Computer Science 1 Honors. Today we're going to be starting to look at searching and sorting from an algorithmic perspective as well as a practical perspective. So remember that we are live on the Piazza Q&A. I will not be looking at the chat on YouTube, however, of course, because of limited bandwidth. So once it stabilizes, there we go. All right, so back to searching and sorting. Basically, the reason we look at these two things is because they are fundamental to any data processing in computer science. Anytime that you want, most algorithms, most more complex algorithms will end up wanting to sort something as a first step and then go on and do something with it because that's structure. Having something that is sorted means that there's structure there, and that structure is often something that you can exploit for more efficient algorithms. And so it forms the basis of for a lot of other algorithms, and it's just basically a common operation. Think about an Excel file and keeping track of a bunch of things in an Excel file. You often filter at the top, or you often sort by this column, or then sort by this column, or then some combination, sort by this column and then by this column, breaking ties. And a large variety of algorithms have been developed for these two basic operations, which gives us an opportunity to start looking at algorithms, algorithm analysis, and some notion of efficiency. All right. To start out with, let's go ahead and start out with the easier one, searching. And we're going to start out with an algorithm called linear search. All right. Now, here's the basic idea. Let me go ahead and give myself some more room down here. There we go. All right, so here's the basic idea. Just given a collection of elements and a key element, K, search through the collection to find any any element that matches K. Now, I was being intentionally vague here, right? You've got a lot of considerations here. Basically, what are you searching, right? Is it an array, right? A list, right? Since we're in Java, a list, etc., right? What is it a collection of, right? Could it be integers, doubles, strings? Yesterday we were doing airports. I think we were doing films in this class, right? Films, etc. Right? And also, how are you searching, right? By what criteria do you mean? Can you determine that you've found a match, right? And there could be many answers to this one, right? If it's searching for an integer, well, of course, I'm searching for 42, right? Well, here's 42. But if it's something more complex, like a film, are you searching for a film with a particular title? Are you searching for a film with a particular IMDb rating, right? Or maybe you're searching for the maximally rated film of all time, right? The one with the highest rating. So you could be searching for a particular element, or the last element, or the first, or the last, the max, or the min, right? Or all elements that match your search criteria. Right? These are all very important questions when you actually go to program something like this. But what I want to do is I want to look at this from a more general algorithmic perspective. We don't want to focus on the details. We want to keep this general, right? We want to develop an algorithm. An algorithm is a finite description of the step-by-step process for computing, for solving a problem, right? That's the dictionary definition. And these are all important questions that we've asked when we actually go to program it, which we will be doing here in a second. But more generally, we want to keep this general. We don't want to get a specific, if we're going to solve a general problem, we're going to want to present this much more abstractly, from an abstract perspective. And to do that, we use a tool called pseudocode. Pseudocode, right? Algorithms, in general, are usually presented using pseudocode. If you're not familiar with the I think it's Latin, but I'm not sure. Pseudo is fake code, right? Code that presents that describes a process at a high level, right? Generally, you make use of English and math. Makes use of English, plain old English, and mathematical symbols. Right? It generally does not use language-specific constructs. Right? So you can write for loops, but you don't necessarily have to end every line with a semicolon or something like that. And in fact, you don't want to do that because then that ties it too closely to a language. It's pseudocode. It's not real code. Now, there are no hard and fast rules for writing good pseudocode. There are just general guidelines, because if there were hard and fast rules for writing pseudocode, guess what? You have a programming language there, right? So let's take a look at this problem from a more general perspective, and also develop an algorithm for it. And in fact, you've already done this. If you remember back on homework 4, we gave you an array of integers, and you simply had to search through it and find out if it contains a particular element, right? So the basic idea with this first algorithm is exhaustively search the collection until you find an element that matches your key. Right? Now, usually we call these needles and haystacks. You have a haystack that you're searching through. That's the collection, and you're searching for a particular needle in there. A needle that matches your key. Right? So I'm not going to go ahead and write it out entirely. In fact, if I started to write it out entirely, it would look more like Python or something like that. So I'm going to pull the pseudocode for this algorithm from the book. Right? And here it is. It's called linear search, and we'll find out why it's called linear search in a moment. We clearly label the input, we clearly label the output. And the input here is a collection of elements, and we even give the collection a name, A, and we also give the elements in the collection names, A1 through AN, and we give the key a name. Element of K is just going to be E sub K, right? Now notice here that I did not use language-specific constructs. I said that it was a collection. I didn't say that it was an array or a list or a set, right? I didn't say that they were integers or doubles or strings or anything else like that. I kept it general. I also didn't use the typical programming language construct of starting at 0. I've started at 1, which is more of a mathematical idea, right? Our output here is an element A in A, such that A is equal to E sub K. Now, what does it mean to be equal? Well, if these were integers and this was a programming language, it would be equals equals if they have the same value. If they were films, what does it mean for this film to be equal to this film? They have the same title, they have the same ID, they have the same director, right? There are lots of different criteria, so that's why we say according to some criteria. Now, we do need to take care of the case where we've got an unsuccessful search. It is possible that we search through the collection and we don't find what we're looking for, that it's not in there. And so what you did in homework 4 is at the end you return false. This array does not contain that element, right? Here we're going to return a flag value, and for that I've simply chosen the mathematical symbol phi, right? The Greek letter phi. That usually is used to denote nothing. I didn't return null. I didn't return false. I didn't return a special other flag integer value or something like that. I am using the more mathematical, general abstract idea of just some flag value. I've got a for each loop. That's not seen in any of the programming languages that we've used so far, except for Java has an enhanced for loop, but it doesn't use the keyword for. And I'm making liberal use here of plain old English. For each element ace of I in the collection A. I didn't set up an index variable, initialize it as 0, and while it's less than the size of this, less than n I plus plus, right? I didn't do that because that would be too much of a specific programming language construct, right? That would tie us to a particular language. The whole point of pseudocode is that you keep it general and abstract, so that then you can take it and you've solved that problem for once and for all, and now you can go ahead and take and make an actual implementation of it in any language, right? This is kind of a blueprint out of which you can then write some Python code, or you can write some Java code, or you can write some C code, which we'll be doing here in a second. Otherwise, we simply ask, is it if that element is equal to the key, then we stop and we output ace of I. We don't return it because that would mean that we're writing a function in C or Java. At the end, if we get through all the elements and we don't find what we're looking for, we output this special flag value. That's our pseudocode, okay? Now, if we're actually going to program this, then we start to have to start answering these questions. How are you going to search? What are you searching? Right? And we're going to have to actually write code to do all this. So let's go ahead and do that. I've got some code set up here. Let me go ahead and increase the size a little bit. There we go. And we've got an array here. This is an array that I'll be using here for another demonstration. And let's go ahead and make a linear search function. Linear search. Right? What would that look like? So again, let's go ahead and do some documentation here first. And let's go ahead and we're going to call it linear search, and we'll find out why it's called linear search in a moment. But it's going to take, now we're in the C world. Now what are we going to be searching? Well, I've got an array down here of integers, so obviously we're going to be searching an array of integers, and we're not going to be making any changes to it. So what do I need to pass to the function? Const int star array. In C, I also need to pass the size of the array in because I need to do manual bookkeeping. So int n will be the size of our array. Okay. Finally, also we need to pass in the key element, the thing that we're searching for. Right? And we can proceed from here. Now here's where the documentation comes in. What are we going to return? How do we indicate a successful search? We could return the element, right? So you search around for 2. Okay, I found it. It's in the first element here. So here you go. Here's 2. That doesn't really give us that much information other than we found what we're looking for. I might as well have returned true or false. And that's another option, and that's the option that you did on your homework in homework 4. It returned an integer value that returned true or false based on whether or not this array contained that element. Right? What I want to do is I want to give a little bit more information. I want to give the index at which I found it. So this function searches the given array of integers for a value matching the given key value. If for the first, if such a value is found, this function returns the index at which it finds it. And the way that I'm going to work this algorithm is I'm going to start at the beginning of the array and go all the way to the end. So I'm going to actually, if there are multiple elements, like there are down here, there's 2 5s, then I'm going to return the index at which I first find it. Because once I found one, well, you just asked for one, not all of them. There's no point in me going and finding the other one as well. I'm going to stop my computation and give you that element, right? This function returns an index at which it finds it first found, right? Upon an unsuccessful search, this function returns ... Now, I can't return fee because there is no fee, right? I can't say return fee because that's a program. That's not a programming language concept. I could define the notion of fee or something like that. Could I return null? Well, yeah, but then that would conflict with the documentation that I've written up here. This is going to end up returning an index value, which means that it's an int. It's not a pointer, right? So what could I return here upon an unsuccessful search? I would need a special value that said, no, this is not in the array. Well, if I return 0, that means that I'm finding it at the first element. In fact, that's what we're going to search for first here. I've searched for 2. you get lucky and you find it at the first index. If I'm returning 0, I didn't find it, then how do I distinguish between a successful search that you found it at 0 versus an unsuccessful search that this is the flag value? So 0 is probably not an ideal value. However, an ideal value here would be, say, -1. Any value that is not a valid index. Okay. So now let's go ahead and write this function. Right? And for that, I'm just going to simply take this and I'm going to transcribe it into C. Right? For int I equals 0, I is less than n, I plus plus. If the ith value is equal to the key, and there's our search criteria, because we know that these are integers, and this is an integer, then we can use the equals operator here to determine whether or not they're equal. And if that's so, then I immediately stop and I can return the index at which I found it, which is going to be I. Otherwise, based on an unsuccessful search, instead of returning a phi, I will return -1. That's a good first design. Let's actually go ahead and test it to make sure that that it's correct. And when I run this, remember, I've set this experiment up so that I'm searching this array. It has 9 elements, and I'm searching for the key element 2. We're going to end up getting lucky here and searching for it and finding it at the first index. So we should expect 0 back here. Oops. There we go. Found 2 at index 0. Okay, great. All right. Let's search for something else. Let's search for, say, 5. Remember, it returns the first element at which first index at which it finds it. So 0, 1, 2 is what we would expect. And we did that successfully. Let's search for 8, something that is towards the end. Right? And that's at index 7. That's the 8th element. 8 is at 8, but it's at index 7 because, of course, we start at 0. We also need to test for an unsuccessful search. Now, of course, I would need to modify my print statement here because if it's an unsuccessful search, it didn't find it. But we can go ahead and reuse this for ad hoc testing purposes, and we would expect -1 because it's an unsuccessful search. All right, that's a pretty good first attempt at linear search here because it's correct. It's reasonably well designed, and I'm going to make sure that you have it in your notes here. Right. But what's another alternative way that we could have done this, right? Instead of returning -1, maybe I could return a pointer value instead, right? What would that look like instead? We could have a return type of int star. This searches the given array of integers for a value matching the given key value. If such a value is found, this function returns a pointer to it in the array. Upon an unsuccessful search, now because we are returning a pointer, we can use that notion of it returns null based on an unsuccessful search. What would that look like now? So we're not going to return I in this case. Instead, we're going to return ARR sub I. That's the value stored at that location. I want to return the pointer to that value, ARR sub I. I want to return a pointer to that memory location. So how do I take, this is just a regular old integer variable. How do I take a regular old integer variable and convert it into a pointer? By putting an ampersand in front of it. And instead of -1, I would return null. Okay? How would I modify my code down here now in order to accommodate this new pattern? Well, I'll just call it P because it's a pointer. And instead of printing this out, I'll print, I found blank at memory address. And to print a pointer, it's going to be %P. And so I found whatever it is at that memory location. Dereferencing that pointer will mean that I get the element stored at that memory location that it's pointing to. And then using P here will mean that I can print out the memory address. And let's search for something that we know is... Oops. That's just a warning. Don't worry about it. We're we're kind of breaking our promise here. That's okay. I'll show you a better way of doing this without tangentially violating that promise. Oh, darn it. Segmentation fault. 42. All right, fine. We're going to have to do this a little bit differently. Darn it. Return null. Do I want to do this? It should be valid here. Found blank at memory location. I don't think that it's because of this, but so be it. Let's try another one. Int star p equals array. And then we'll return blah, blah, blah. We'll return... sorry about this. Let's go ahead and change gears here for a moment. And I'm going to go ahead and back up. I'll come back to that later. Okay, there we go. GCC. Let's make sure that we've backed up properly. Okay, we're good to go here now. What I wanted to do first is something a little bit different. Then we'll come back to that. Sorry. So this is a linear search, but what is it good for, right? What is it? It's good for arrays of integers, right? The above is only good for arrays of integers. What if we now wanted an implementation for, say, double values? All right, let's go ahead and copy paste this. Right. So I want to keep this this original one here. And we can't name it linear search anymore. Instead, I would need to name it linear search for doubles or something like that. How would it look different? Well, the search is the given array of doubles for a value matching the given key value. If such a value is found, the function returns an index at which it found it. Otherwise, it returns -1 for an unsuccessful search. So the only way that this changes is the values here, double and double. It has to be an array of doubles, and then of course my key value has to be a double as well. Otherwise the code doesn't change here at all, right? So this nothing in here changes at all, right? What if we wanted to have a linear search for films, right? What would that look like? And once again, let me go ahead and copy paste this, right? Searches the given array of films, right, for a value matching the given key value. If such a value is found, then the function returns an index at which it found, blah, blah, blah. It has the same basic, I mean, it's linear search, right? It's a general search algorithm. So it's linear search for films, right, or film. Now it's no longer a double, it's a film, and we can bring that in later on for demonstration purposes. And your key is also a film, right? Because you are those two do generally need to match. Of course, you could, if you have a different criteria, you could say, I want to search for a film with a particular title, and then in which case you would pass in a char star containing the title that you're looking for. You would still iterate over each element. The only difference here is your search criteria, right? If the film at array of I has the same title as the title in key, right, then I return I. Right? Now, of course, this is not real code here. How would we end up doing this? If you remember our definition of film, we had a title. So if I've got a regular old structure here, the ith film, it has a title value, and the key has a title value. Right? Of course, I could change it so that this is a pointer. I won't do that yet. I could change this so that this is an array of pointer. I won't do that yet either. So the same title is equals this. Well, I've got a string over here and a string over here. How would I end up making this comparison? strcmp. Compare that title to this title. And if they're the same, then strcmp returns 0, and I do have to check for that. Right? There was a question the other day on Piazza about why is this not working? It's because you weren't they weren't looking for 0, right? 0 is false. So if you just have this, then that's going to be this title matches this title false. We were and that if statement will never execute. It'll never return I. So what you need to do is you need to check, is it equal to 0, right? But otherwise, it's the exact same code, exact same code, exact same code, right? The only difference is your parameters and your search criteria, right? I'm going to go ahead and make sure that you have those examples. Of course, you'd have to bring in the film structure that we defined last week or a couple weeks ago or something like that. But here's the problem: is we're violating the DRY principle. Don't repeat yourself principle, right? All of these are the same implementation of the linear search algorithm. The only difference is their parameters and their search criteria. For numbers, you use equals equals. For strings, you would end up using strcmp. And for more complex structures, you would end up using a combination, whatever your search criteria is title, IMDb rating, whatever, you'd have to put that logic right here. But otherwise, the algorithm is exactly the same. Wouldn't it be nice if we could write one linear search algorithm, one linear search function to handle any type? Our eventual goal will be to create one function, one implementation of a search algorithm that can be used for any type of variable. The problem is that you still need to specify a search criteria. All right? The way that this is going to work is that we're going to make this generic. That we're not going to be passing in integers. We're not going to be passing in doubles. We're not going to be passing in films. Instead, we're going to be passing in elements. Now in C, that means that we're going to introduce void pointers. In Java, that means that we're going to be introducing parameterization. But it can be done. It's just any old type, right? It could be integers, it could be doubles, it could be strings. But given these two things, the algorithm still needs to say, is this it? Right? Are these two things equal? Is this what you're searching for? So we need another component besides the array, besides the size of the array, and besides the key value that we're searching for. We need to bring in something called a comparator. All right. So eventually we're going to introduce the notion of a comparator in order to determine if an element is equal, or more generally, the relative order of elements, right? We'll use comparators. Right? Comparator functions in comparators. There we go. Comparator functions in C, comparators in Java. It's a class. It's an entire class. Basically, we've seen this pattern before. In fact, we saw it right here. strcmp. Remember what it returns. If I've got a string apple and banana, then these are in order, so it will return something negative. If I've got banana and apple, they're out of order, right? So it will return something positive. If I've got apple and apple, I'm comparing apple to apple, they're equal, and it'll return 0. It returns something negative, positive, or 0, depending on the relative ordering of things. And by using that pattern, we can actually make our code generic, and we only ever have to write one function to rule them all in order to do linear search on any type of variable that you would want now or in the future. Right? All you need to do, instead of rewriting the algorithm over and over and over again like we just demonstrated, all you would have to do is write a new comparator and then give it to the same implementation. Okay? Before we get there, though, I want to look and see if there's a better solution here. Right? So let's take a look at an analysis here. Right? An analysis of the linear search algorithm. In the best case, how much work or resources or computation time does linear search take? Right? Well, we had an array of size n, or 9, so it didn't take any time at all, right? In fact, if I ran this again, I could time it. Time A dot out, right? It wasn't even measurable. The amount of system time was 0 seconds. The amount of real time was 0.002 seconds, which is still not noticeable by most reasonable humans, right? Unless you're really, really quick. So what we need, but if I ran this on an array that was much larger, this is an array of size 9, very, very small, right? So what if I ran it on an array of size 10 billion elements? Obviously, it's probably going to take a little bit more time, right? And it'll probably be more perceptible to humans at that point. It might take a few seconds, or might it take a few days, right? If it's really, really, really large and our search criteria is very, very complex, I don't know. To be able to even look at that and start considering that, we need a notion of what work or resources are. For that, I'm going to go back to our pseudocode here. Now, how would you characterize the work done by this algorithm here? We have a for each loop, right? We have to iterate over each element, but that's kind of part of the control structure of the algorithm itself. That's not where the real work is done. The real work is done when you compare two elements. Given this element and this element, are they equal, right? That's probably the most complex or the most common operation in this entire algorithm. And for an actual implementation, like search for doubles, that means that this comparison right here, right, somewhere in the processor, it is loading the ith element up into memory, into some register. It is loading the key element up into some register, and then it's calling an operation to compare these two and jump to a memory location if they are equal, right? So that's where the real work is being done. Yes, there's work being done for the for loop because you have to maintain, you have to make an addition for every iteration of the loop. You have to check, am I done with a loop by making another comparison? Is I strictly less than or equal or than n or not, right? At which point you stop the algorithm. But really, the real work is being done here with this comparison. You can consider the work being done up here because that is non-trivial. I mean, you do have a processor that is executing commands to do this. But all of those operations are going to be proportional to this operation right here. They're only going to contribute some constant out front of the real work, right? So for searching, comparison, the number of comparisons is a good measure of resources, right? Because it takes, I don't know, say it takes 3 nanoseconds for each comparison. And if we do 50 of those, then that's 150 nanoseconds. It's characterized how much work we're actually doing, how much time we're actually taking to execute this algorithm, right? Not only that, but it starts to really capture the notion of this algorithm because on small arrays, then it's going to take much less time. But on much larger arrays, then that multiplication gets larger, and of course then we can start to notice that. So that this is the correct notion of work as far as our algorithm is concerned. So the question is, how many? So I've changed the question. How many comparisons does linear search make to find an element? Well, it's actually adaptive because if we could get lucky, right? We could get lucky and we find 2 at the first value, right? We ended up making only 1 comparison, right? So in the best case scenario, 1, right? You get lucky and find the element at the first index, right? Well, we can't always be optimists, so we can't think of the best case scenario all the time. Let's go ahead and think in the opposite direction, though. Let's think about the worst case. The worst case scenario would end up being n comparisons. Why? Because you end up searching, if there are, assuming there are n elements in the array, right? Or the collection more generally, right? Why? Because you end up making a comparison with the first one, second one, third one. In order to find 42 over here, we ended up having to compare all of them. So how many of them are there in there? N, or 9 in this case. And so we ended up making 9 comparisons to find that it's not that value is not in the array, right? Or another worst case scenario would be you're searching for the element at the end, and you find it, but it's in the last place that you're looking for, right? So in either case, it's going to be n comparisons, right? You get unlucky and you don't find it on an unsuccessful search, or you find it at the very last element index of the array, right? Well, just as we can't think of the best case scenario all the time, maybe we don't want to be pessimists either and not think about the worst case all the time. You can think about the average case scenario. On average, how many comparisons would a linear search make? Right? And for this one, it's a little bit more complicated of an analysis. You'd have to define a probability distribution on a successful search and an unsuccessful search, and based on a successful search, you would consider a uniform probability distribution on the rest of the elements. Blah 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 blah. You come up with basically the same answer as doing it naively. The naive way of doing this is to look at the best case scenario and the worst case scenario and simply average them together, right? So it's going to end up being approximately, I'll go into math mode here. It's going to end up being approximately n divided by 2. Right? In fact, I can nicely format this. N divided by 2. Right? On average. Right? And that's because n plus 1 divided by 2, drop the half so that we don't have to worry about those that lower order value. Right? So we've got an average case scenario that on average we're going to take about n divided by 2. Now what about the comparing the worst case and the average case scenario here, right? If I go to Wolfram Alpha and I look to graph these, right? F of n is equal to n, g of n is equal to n divided by 2. And let's go ahead and plot these. N greater than or equal to 0. I'm only going to do that so that we have a nice plot. N here is basically the size of the array, and you can't have any negatively sized arrays, right? It's not going to let me plot just like that. Oh, maybe because of that. You should be able to plot this, but it is taking forever. All right. But in any case, it's going to look like, there we go. Both of these functions are linear functions. They grow linearly, right? So this one has a little bit less of a slope to it because of 1/2. There's a 1/2 coefficient sitting out front. But at the end of the day, if you add more, if you're searching a larger and larger array, then you're going to end up with more and more resources being taken, more and more time, right? It doesn't matter if you look at the average case or the worst case. Both of these are linear functions, right? Both the worst and average case are linear functions, right? Linear search makes a linear number of comparisons with respect to the input size, right? The size n being the number of elements in the array or in the collection more generally, right? So that's why we call it linear search. That's not bad. In fact, if you can make no other assumptions on your array or on your input, then this is basically the best that you can do, more or less. But think about this in terms of ever larger arrays, right? Suppose that linear search takes t time, right, seconds or whatever, however you're measuring, nanoseconds, milliseconds, whatever, time to search an array of size n, right? Now suppose you double the input size, right? You go from n to 2n, right? Then how much time would you expect it to take now? Well, if it took t time before, it now takes 2t time to search, right? In other words, doubling the input size doubles the time, right? It grows linearly with respect to the complexity of the algorithm. Okay. All right. Can we do better? Can we do better? Right. Yes. So we're going to introduce binary search here. Suppose that the input array is sorted. Right? So being sorted gives the array structure. Structure can be exploited in some manner. Okay? Now, let's take a look at an array here. Here's the idea behind binary search. Suppose that this array is sorted. We've got A1, A2, A3, ... all the way up to AN. All right? And I'm going to be searching throughout this for a value of, say, 42. Okay? Let's go ahead and immediately look at the middle element here. The element at index n divided by 2, roughly. Right? Again, this is more mathematical. This is a sub 1 and a sub n. So the element at the middle index is going to be n divided by 2. Okay, we're going to have to take care of that when we actually program this, but so be it. Suppose that value is m. And remember, I'm searching for 42. Now, if m is equal to 42, I'm done. I found what I was looking for. Just like I got lucky with linear search and I found it at the first index that I was looking for. If I jump to the middle and I find what I'm looking for, then I know that then I'm done and I can quit, right? But if that's not the element that I'm looking for, then I make a comparison. Everything over here is less than m. Everything over here is greater than m. So if 42 is less than m, then I know that if it exists in this array, it exists in the left half. If 42 is greater than m, then I know that if it exists in this half over here. In either case, I've cut down my work. I've cut down the work in half by making only one comparison, right? I've basically, with one comparison, I'm able to cut it in half and throw this half away, or throw this half away. Now I can repeat on that half. Now that I've thrown this half away, I only have to search this half. Look at the middle element again, splitting it into two partitions, and repeat. Now maybe I throw this half away instead. So if I started out with 8 elements, I'm now down to 4 elements, now down to 2 elements, now down to 1 element, right? And if that's the element I'm looking for, then I'm done. I had to make all those comparisons to get down there. Otherwise, if I have 0 elements now I know I'm done because it's an unsuccessful search. You didn't find what you were looking for. It is all dependent on the fact that this is sorted. And if this is not sorted, then of course it's not going to work. Okay, that's the idea of binary search. What we do is you look at the middle element. Right? If it is equal to your key, you are done. Right? Stop the search. Success. Right? Return the index at which you found it. If the key is less than the middle element, right? In other words, k is less than m. The middle element m, we'll give that a name m, and we're searching for the key k. Search for the key k in a sorted array. If the key is less than the middle element, then search in the lower half, or lower or / left half. Right? If the key is greater than the middle element, in other words, m is less than k, then search in the upper or right half. Right? Until you either find it or you have an array that you've just chopped it in half, 8 goes down to 4, 4 goes down to 2, 2 goes down to 1. 1 divided by 2 is going to end up being an empty array, right? Because for truncation is how we're going to exploit that. Until you either find it or you have an array of size 0, right? Unsuccessful search. Now, inherently, this is a divide and conquer approach. You look at the middle element and you throw away half of it. Right? You're dividing it and conquering it. I've conquered this half because I know that if the key exists, it exists in this half, and I can automatically throw that away. I've divided it, and I've conquered it by throwing it away. Now I'll conquer this half. Divide it again, and throw away half of it. Divide it again, and throw away half of it until you're down to either one element. Right? So this is a divide and conquer style algorithm that may be implemented recursively, right? How would you do this recursively? All right, well, you'd call it with an array of a particular size. You'd want to maintain index values, I and j, right? And then you would, if you would search and look at the middle element, and if that's not the element that you're looking, if it's the element that you're looking for, then you immediately return. Otherwise, you make a recursive call on either this half or a recursive call on this half. Right? We're not going to do it that way. Again, I illustrated with our coverage of recursion that there's always an iterative version of this idea instead, and that's what we're going to do today. We're going to implement an iterative version of this instead. Okay. So let's go over here to our code. I'll go ahead and add to do documentation. Right? Same documentation as before. We're going to return the index at which we find it, and we're going to call this binary search. And it takes a const int star array, int n, the size of the array, and int key, the element that you're searching for. Same exact signature as linear search. Now, I need to set myself up. Right? Now, initially, I'm going to be looking at the first element. In this case, it's 1, but in our case, it's going to be 0. And I'm going to be looking between the first element and the last element. It was in this case 1 and n, but in our case, it's going to be 0 and n minus 1. So I'm going to create some index values. Int left is going to start at 0, and int right is going to start at n minus 1. Right? Just to keep track of where I am. And what I'm going to do is I'm going to update these index variables. By cutting out this half of the list, I'm going to update the left index. By cutting out this half of the list, I'm going to end up decrementing the right index value. Okay. Now let's go ahead and implement this idea. Look at the middle element m. Right? Well, how do you get m? Well, in general, if it would have been on the first iteration, it's going to be n divided by 2. But in general, if I've got I and j, or if I've got left and right, the middle element between these two values is simply the average of them. So let's go ahead and compute the average. It is equal to left plus right divided by 2. Right? Careful. Right? This risks overflow. Right? I can't tell you how many times I've seen tutorials online. The tutorials online are going to try to keep it simple, and I'm going to keep it simple now too. But this is not the way to do this. In fact, there is a bug in the Java in the Java library, this very bug here that risked overflow on very, very large arrays. Because what I'm doing is I'm taking, suppose that these are very, very large numbers, say 2 billion and 2 billion and 2 billion 100. Right? 2 billion plus 2 billion 100, that is going to be overflow because that's 4 billion. But the middle element that we're computing, that's not overflow. That's 2 billion plus 50, somewhere in between there, right? So the real solution here is to take the left, let's say the right minus left. That will give you the difference. Divide that by 2, and then plus left to get back to where you were. And that's the real way of doing this. In fact, you can do it by shifting things over instead of dividing by 2, and it's even more efficient. Don't worry about that. I just mentioned that to show that I am not incompetent, that I do know that there is an overflow risk here. I'm just going to keep it simple, though. All right. What we want is the middle index. All right. Now, if the key is less than m, then I need to search in the left half. Right? To do that, I've got my left, I've got my right, and I've got my middle over here. I need to search in the left half of the index, this meaning that I'm going to shift my right index over to, let's take this example here. If I'm going to, if the key is less than M, that means I search in this half over here. I take my right index that was over here and I update it to one right below the middle index over here. Why? Well, we've already we need to compare the middle element here, so I guess that's what I should have done first, right? Let's go ahead and do that now. If the key is equal to the element at the mth index, then successful search and return M. Remember, we're returning the index at which we find it. We found it because the key is equal to the element at the mth index. Otherwise, there we go. If the key is less than M, then I search in the left half. To do that, I just update the right index. Right? I'm going to shift it. I'm going to shift that right index down. Right? Right is equal to M minus 1. Why not just M? Well, because I've already compared the element at index M. There's no need to compare it again. So I'll just go down one less than that. Likewise, for symmetry, else if the key is greater than M, key, there we go, right? Then search in the right half, right? Update the left index. Left is going to end up being M plus 1. Again, visually over here, we're going to want this element over here. So if this is M, then M plus 1, that's where we go to get the left index and then the right index. Now we're only searching on this upper half, all right? On the right half, the upper half. Left is the lower half, right? Now that was only one iteration. I need to make sure that I continue this while some condition I continue updating my left index. I continue updating my right index, left, right, until we either get down to one element, in which case I would still want to make one more iteration because I still need to make sure that I'm comparing that element. If I'm just down to an array of size 1, I want to know, is that the thing that I'm looking for? So when do I actually stop for an unsuccessful search? When these two indices have passed each other. Right? So while left is less than or equal to right, keep going. Keep doing this iteration of left, right, right? And that's it. At the end, I return -1 for an unsuccessful search. And let's go ahead and clean it up. Demo.c. There we go. And there's my indentation cleanup. Okay? Pretty good. Let's go ahead and make sure that it actually works. Binary search. Now, is it going to work on this array that we were using before? Let's find out. 2. GCC. Gets stuck in an infinite loop. I wonder why. Let's go ahead and search for something that doesn't exist. 42. Well, it works, right? No, it doesn't work in general because this is not sorted, right? Remember that binary search requires the array to be sorted. Here are the same elements sorted. Let's see if it works now or if I've got some... there we go. Found 2 at index 1, right there. This is index 0, this is index 1. So that works. Let's try finding something at the extreme part. Let's say 1 is at index 0. Oops. We've got an infinite loop here. If the key is less than M, then right goes down to M minus 1. If the key is greater than left, and updates to that. We should be good. Left press the right. Somebody help me out online. If not, that's okay. Let's go ahead and try something else here first. What about 8 on the other end? Okay, that finds it at index 8 all the way down here. Remember, it's the 9th element, so that's at index 8. That works. Let's do an unsuccessful search again. I think we already did this, but There we go. Found at index 1. Okay. Well, this is a good opportunity to go ahead and review GDB. Yeah, we've got time. So let's go ahead and GCC this. Remember, to use GDB, you're going to have to use the G flag, demo.c. Right? And let's make sure that we've got an infinite loop here. Good. All right. Let's go ahead and run this. GDB a.out. All right. Run. All right. Now we're stuck in this infinite loop, but I'm going to go ahead and kill the program. That only pauses it, by the way. And layout next. Let's see why we're stuck in this. So I can print left, I can print right, and they're both, so 0 and 3. Okay, so next, print key. Remember the key is 1 here. Okay, so this is print M now. All right, that's at 1 because of 3 and 0. It's going to be 3 divided by 2. Truncation is going to make that 1. Okay. So this is not going to be true. All right. And the key is less than M if we print. Oh, that's my problem. I'm glad that I realized this. What am I doing? I'm comparing it to the element in the array. Here, I'm comparing it to the index, not the element. So I've already found my error. Let's go ahead and quit. Right. There we go. And let's go back up here and fix it. Right. So I shouldn't be comparing it to the index. I should be comparing it to the element stored at that index. And both of those were wrong. Sorry about that. Let's go ahead. Oops. I want GCC. Let's run that again on, what are we running it on? 1. And that should find it at index 0. Great, we did it. Let's go ahead and do some regression here. Make sure that we didn't break anything. That was working before. Great. And this is an unsuccessful search. We need to make sure that that's also working. Great. All those things are now working. Right? Didn't take as much time as I thought it would. So let's go ahead and analyze this one. Right? In fact, I'll go ahead and make sure that you have this in your notes. But of course, it's in the book. And by the way, we haven't really used anything that is C specific except for the function prototype or the function signatures here. In fact, I think that everything in here would be exactly the same if we were using arrays in Java. Right? So there's no point in looking at this in Java. Instead, we'll look at how to do this even better in both languages on Thursday. Okay? But let's analyze this now. Right? Analysis. Right? So binary search actually only makes about approximately log base 2 of n comparisons in the worst. Okay, good. Hopefully it wasn't dropped for too long there. Hopefully it only dropped for like 2 seconds there. But in any case, I do have recordings of this, and we've got pre-prepared videos anyway if we need a backup here. But as I was saying, that binary search only makes a logarithmic number of comparisons in the worst and average case for arrays or collections of with n elements in them. Right? How much better is this than linear search? So let's look at it from the same perspective as before. Or let's actually look at it from one perspective. Suppose you have an array of 1 trillion elements. Right? That is, 1 trillion is going to be Wolfram alpha 10 to the 6th. That's million, billion. There's a trillion. Right? That's your n. How many comparisons are you going to end up making with linear search? So linear search will end up making 1 trillion or 500 billion in the average comparisons. So 1 trillion is the worst case scenario where you don't find what you're looking for. 500 billion in the average case. But binary search will end up making log base 2 of 10 to the 12 comparisons. Sorry, there we go. There. All right. Get rid of that there. Okay, good. What is that? Wolfram alpha. Log base 2 of this. Now, before I type this out, remember your logarithmic identities, that the exponent can come out front. And this ends up only being about less than 40 comparisons, right? So it's going to be less than or equal to 40 comparisons, right? Astronomically lower. 1 trillion versus 40, right? Binary search is definitely going to blow linear search away. Like there's no contest here, right? I'll look at it from another perspective. Suppose it takes n comparison, let's say t time, to compute perform binary search on an array of size n, right? Now let's do the same trick as we did before of doubling the input size. Doubling the input size, right? In other words, going from n to 2n means you now have log base 2 of n 2n comparisons. All right? Well, again, logarithmic identities. What can you do with that? Log of base 2 of a times b, you can split that up into 2 logs. That's going to be log base 2 of n plus log base 2 of 2, right? Which is equal to, that second one can be simplified. Sorry, log and log. That second one can be greatly simplified. In fact, log base 2 of 2 is simply just 1. So plus 1. There we go. That's it. In other words, in other words, doubling the input size means you only need 1 more comparison. Right? It does not grow linearly. So let's go back and plot those two things again. Plot f of n is equal to n. G of n is equal to log base 2 of n. Right? Oops. Now, the idea here with why base 2 while this is loading. Base 2 because... why are you not doing... There, I wanted both. Why base 2? Because it basically halves it each time. If you start out with n, then the next iteration you have n divided by 2. N divided by 2 again is n divided by 4. N divided by 8. So in the denominator down there, it's growing exponentially. And so when you take the inverse of that and solve for how many iterations do you have to do to get down to 1, that's where you get the log base 2. It's cutting it in half each and every single time. There is something called ternary search where you can split it up into 3 parts every time, but it's basically the same thing, all right? Asymptotically, algorithmically, right? Now, I don't know how to get n equals 0, 1 up to, I don't know, let's 10 trillion, right? Let's see, let's look at these 2 plots. There we go. Yeah, it might be difficult to see here, but this blue line here, that's linear search, right? Of course, it's growing linearly. So you would expect to make about 1 trillion comparisons when your input size is 1 trillion. What about binary search? It's so flat at this scale, it seems like it's almost 0, right? And remember that it's only 40. 40 versus 1 trillion, right? There's no contest here at all, right? That binary search is exponentially faster than linear search, right? So if you were to do this in practice, of course, your choice is, yeah, binary search, no contest there. But binary search requires that the input be sorted, right? And that's our next topic. How do we actually get to that point where something is already sorted, right? Sorting may be expensive, but it also may be an investment. If you're going to be searching through this list a lot, over and over and over again, sorting it definitely will help you, because once you paid that upfront cost to sort it, and maybe even maintain that ordering depending on the data structure, then the savings later on of searching it over and over and over again, using a minuscule number of comparisons, it doesn't compare at all. That's why I call it an investment. So for the next 2.5 weeks, what we're going to be doing, well, next 2 weeks, because we'll have a review at the end, but for the next 2 weeks, we'll be continuing this. We still have some loose ends here. For example, how do I only do one version of linear search or one version of binary search to rule them all? So using a comparator. How do I actually start sorting? And we're going to look at several sorting algorithms. How can I use these two ideas to solve a real problem? And at the end of the day, how can I avoid writing my own searching and sorting functions like I was doing today? I use what's built into the standards library. In C, that's in the standard library, or there's a standard search library. In Java, it's in the collections library. Don't write your own binary search. Use what's already there. Okay? All right. Then no questions online. Hopefully everything worked out here. Otherwise, I'll see you back in Louise Pound on Thursday. Have a good day.